So the last 2 weeks we talked about dark energy. I'm going to go start to delve into dark matter, which is going to be our topic for the rest of this lecture series. And I'm going to harken back to some of the things I talked about in the first lecture, which is how we study the universe with light, and now focusing on how we can understand the dark side of the universe, specifically with light. The topic today is actually going to be studying dark matter actually with gravity instead of light. What is the gravitational effect of dark matter? How does this control how our universe evolves, how our galaxy evolves, how we interact with the galaxy around us, etc. So let's see. This was working. Okay, there we go. This thing has to be a miracle today and reach way back to there. So, okay. So how do we know that there is dark matter, right? How do we know that dark matter is some sort of new particle that we're missing and it's not part of the standard model that we can interact with? And how can we test the properties of dark matter with its gravitational force, right? Instead of looking for it as a particle, how can we just look at the gravity of dark matter overall and test the characteristics of dark matter? There we go. So remember from the first lecture that we observed the dark side of the universe with light. And what we want to study here today is how dark matter affects the parts of the universe that we can't observe, because we can't observe dark matter directly. We can't observe the light directly. So dark matter has to affect something that makes light, and then we can see how that light changes based on the effect of dark matter. So think for a minute about back to a playground as a child, and you're holding onto a merry-go-round. And a merry-go-round starts spinning faster and faster as some larger kid pushes it. And you have to hold on tighter and tighter to not fly off the side and get made fun of or land in a mud puddle or something like that, right? This is gives you some sort of equality between a force, the force that's pushing you off this merry-go-round, and the force that you have to hold on with, right, to stay in a circular formation. The same thing is true of, say, the planets in our solar system, right? They're swinging around really fast, and something has to be holding them in. And that thing that's holding them is the gravitational force from the sun. It's pulling these planets back towards the sun. They're moving in this direction, and that makes a circular orbit that the planets all have. Right? That's how we can study, the mass of the sun itself. How do you calculate the mass of the sun? Well, you see how far all these planets are away and how fast they're moving, and the force from the sun has to be the thing that's holding them into this circular orbit, and that's how you calculate the mass of the sun. Okay. You can try to do the same thing for galaxy clusters. This was first done by Fritz Zwicky in the 1930s. He's here looking quite neat. That was his normal state of looking. So Fritz Zwicky was the first to look at the Coma cluster, which is a large cluster with thousands upon thousands of galaxies in it. So all these galaxies are orbiting this massive center here, which is, it turns out, mostly dark matter. He didn't know that at the time. And he said, well, I counted up all the mass of these different galaxies, and there's not enough mass here to keep the galaxies moving in a circle, right? I counted up the sun's mass, and it's not massive enough to hold all the planets in, so there has to be something else. But this is now for clusters of galaxies. And he said that all the stuff I could see was only 1/400th of the total mass. So I needed something else to supply a lot more mass. I'll call that Dunkel materie, if I can pronounce languages correctly. This has to be some dark matter. So he was the first to give it the name dark matter. One problem was that Fritz Zwicky was widely known for being a crazy person who came up with lots of crazy theories. A lot of them ended up being right, so he's pretty famous. A lot of them ended up being wrong, so it wasn't widely followed up, all his theories at the time. And also, he was kind of hard to deal with, so a lot of people just ignored him. Also, it turns out he was mostly wrong. He said the dark matter was 400 times more massive than the luminous matter. Turns out the answer is only 5 times as luminous. So he was wrong by a factor of 100, but then right by a factor of 5, so that makes him famous. And he put a slide on that, right? Okay, so this was widely ignored for about 40 to 50 years, until Vera Rubin, shown here, started measuring the Andromeda Galaxy, which is a nearby galaxy to us, the nearest large galaxy. And she measured the rotational velocity of all these different stars shown here in black around the center of this galaxy. And she came to the same conclusion, right? There wasn't enough light matter that she could see to account for the velocity of all these stars, especially the stars that were way out here in the outskirts. So what she actually said is right around it here worked pretty well. There was a lot of light, and the stars were moving somewhat rapidly, and everything worked out. Out here, there's not a lot of light inside of this, and the stars were still moving really fast. She expected them to be slowing down because they're much farther away from this central light mass. Here's what she actually observed. This is here as a function of the distance between the center of this galaxy and where the stars are. Here's the velocity of the stars. Really close to the center of the galaxy, there's a lot of mass, and everything's really close, it moves quickly. And then she expected things to fall down like this, and instead, the stars continued to rotate really fast, even as you got really far away from the center of the galaxy. So there had to be more mass in this galaxy that was affecting the stars out here. On a modern picture of the galaxy NGC 6503, you can see the contributions from the stars and gas here, and this is the rotational velocity of stars that you would calculate just from the things you can see, right? These rotational velocities, and then some extra rotational velocity that comes from this dark matter halo, which dominates how fast stars move at really high distances away from the center of the galaxy, but is actually somewhat less important really closer to the centers of galaxies. That's because the dark matter halo actually, as we'll find out later, extends farther away from the centers of the galaxies. It's not so peaked towards the center, but it's most of the matter that's farther away. And now let's see if this thing quantifies. Okay, good. So that was one thing that pointed towards dark matter, and that's usually considered the first discovery of dark matter, and people started taking it seriously. That being said, most scientists were less convinced, and some of these other clues were the things that really convinced scientists coming in around the same time or a couple years later. One is called gravitational lensing, right? So we talked in lecture 1 about how you determine that something is in between you and some background light, right? You were looking at a star and some gas moved the way through it, absorbed some light, and then that's how you knew that gas was there. Well, you could do the same thing with gravity, right? If there's some star that's way far away, and you have something move through it that has a lot of mass, that will contort the light that is moving from that distant star to you. And you can see this as a bending of the light around the object. This can be done somewhat impressively in terms of Einstein rings shown here. So there's a background, very bright source out here, maybe a real background galaxy. And then in the middle, there's something that's dark matter directly in front of it. And what happens is, light from this background thing gets deflected as it moves around the dark matter and forms a ring. So some of the light that would have gone this way, would have missed you completely, gets bent by the dark matter and then comes to your telescope. And then some light that was going to go this way was going to miss you over here, but it gets bent back and comes to your telescope. You get this bright ring pattern in the sky. That's an actual image there. That's the best image, which is why it's on this slide, of an Einstein ring, this bright swirling pattern. Now that's called strong gravitational lensing. When it really distorts the object, you see multiple images, or you see a galaxy that gets stretched in this weird pattern. There's also weak gravitational lensing, and this is almost strong gravitational lensing, so you can see it here. So here's a galaxy here. There's some multiple images here. And then if you calculate statistically all of these galaxies here, they still look like normal galaxies individually, but they're all getting pulled in this circular direction here. So if you calculate the average tilt of all these background galaxies, they're all getting pulled in this direction. And that's called weak gravitational lensing. You can't see it in individual galaxies, but you can use computers to calculate what the average direction of galaxies are. Yeah?
The galaxies aren't on the same plane, though. Aren't the faint ones very, very far away?
Yeah. So these galaxies are all really far away, but all the light from all these galaxies passes by some central gravitational force up here. So if you look, and this is actually very interesting, it doesn't matter how close this mass is to you and how close it is to the background galaxy. It just has to be in between you and the galaxy along the line of sight, and it causes this same twisting pattern. Yeah?
So all those are one galaxy. Pictures of one galaxy.
In this one, this is all one galaxy. This one, this ABCD, is all the same galaxy that's been strongly gravitational lensed. And all these things here are different galaxies that are just being weakly lensed. Yeah?
What gives dark matter its mass? Do they have like a Higgs boson or something?
We'll get to that near the end of this lecture. So right now we only know that there's a lot of mass overall in dark matter, but we don't know, is it a bajillion particles with a very small mass, or is it, you know, only a billion particles with a much larger mass? So that's what we'll come to kind of think about here near the end of the lecture. Okay. So we know there's some gravitational lensing, and if you calculate the amount of gravitational lensing in different directions, you'll find lenses where there's no light in between, right? So there was a lot of gravity that was pulling things around, but you couldn't find anything that was light there that would have had that mass. So there must be some extra dark matter doing it. One of the most kind of dramatic discoveries is called the bullet cluster. This is two massive galaxy clusters. Each one has thousands of galaxies along with it, and they crashed into each other at thousands of kilometers per second speed. So you might ask, what will happen when two really massive galaxy clusters crash into each other? Well, in terms of light matter that we can see, there are two major things that make up galaxies and galaxy clusters, right? There are stars and there's gas. And then it turns out there's about 40 times as much gas as there are stars. Well, stars, if they are mostly empty states, right? We're here, the next star over is 4 light years away from us. The next star after that is like 8 light years away. There's a lot of empty space in between those. So stars that are moving very rapidly past each other will just move straight through, right? But gas isn't like that, right? Gas in a room collides and interacts and bounces off and heats up. So you looked at the bullet cluster, called the bullet because they're crashing into each other very fast, and you asked, where is the gas, where is the stars, and where is the mass, right? So this bullet cluster picture here in pink, this is where all the hot gas is, right? The gases crashed into each other, it slowed down, and it started interacting and heating up. Blue, over here and over here, is where you see a lot of gravitational lensing, right? So that's where background galaxies are getting distorted. You don't see any cool Einstein rings in this picture, but you can calculate all the weak lensing of all these background galaxies. So that's where all the mass is. And like I said, gas usually makes up 98% of the mass. Stars aren't important. But the mass has moved out here, which tells us the mass of these galaxy clusters is not in the gas. It's in something new. And that something new doesn't interact. It moves right through like stars do. It doesn't collide collisionally like gas does. So stars and mass out here, gas all on the inside. This is another picture of the same thing. This is the hot gas, and this is where the center of gravitational lensing is on either side. Same picture, basically. Another thing is how the structure of the universe forms overall. So we have lots of structure around us today. There's a star near us, and there's a bunch of planets, and that's a lot of massive structure. But why did all that structure form in the first place? How did we start from a universe that we think was very homogeneous? It was very much the same everywhere, and we collapsed to form the structure we can see today. And I'm going to run up to the back real quick and start a movie, which takes a minute, but it's worth watching. So what you're seeing here as I walk down is a picture of the universe evolving from a state where there are very few fluctuations. Right? Everything was basically smooth and the same everywhere. Yes. So. And then slowly structure starts to form and collapse. First into really small objects. So you can see a bunch of really small objects at different points in these pictures here in kind of a web-like formation. And you're going to see these slowly as this movie continues, collapse into a really big object at the center. And lots of smaller objects are going to start falling in to form bigger objects. This is how our theory says that the universe evolves, right? We start with very small fluctuations, and those are places that are a little bit more massive than other points. And so gravitationally, they pull more mass in close to them, because they're the denser points. And this just continues. You get more and more mass. Basically, the rich become richer. Anything that's massive pulls more mass in close to it, and you get very massive things at the center. We'll just watch here for a minute. So now we're at z equals 2.5. So this is 3 billion years after the Big Bang. Now it's 13 billion years after the Big Bang, so we'll continue to watch this evolve. It will speed up a little bit, so it doesn't take 13 billion years. So now we have a really massive center of, I think, let's see, 500 kiloparsecs, galaxy cluster here in the center. These are all smaller dark matter subhalos, but these all probably contain galaxies, with the very center being the most massive region, very dense in galaxies. I think at some point you might actually see something else big fall in. I don't remember if that happens or not. You can see some like larger galaxy systems out there. Okay. Yay.
Thank you.
Yeah, that's pretty cool.
Thank you.
Okay, we gotta turn the lights back up just a little bit while we finish into this. Maybe. Okay, now we're almost to the present. So the question is, how does that structure form? And like I said, dark matter produces more mass than all the baryons we can see, about 5 times as much. And so dark matter is the dominant gravitational force that is making the ridge richer, that is making things fall into more massive regions. And it turns out, and we'll talk about why in just a second, it's much more effective than baryonic matter, all the normal matter that we can see, at falling in and forming dense clumps, and I'll explain why. Lastly, the cosmic microwave background. And this is connected to the last slide. And I think you've talked about this in quite a few of the recent lectures. But there are anisotropies. There are hot regions of the cosmic microwave background, and there are cold regions. And this plot, which you've been shown, I think, in almost every lecture now, talks about at different angular distances away how correlated a hot region is to another hot region. And how, basically, what are the size and the amplitude of these clumps? How hot do the hot regions get? How far are they away from cold regions? So hot regions are areas where there is extra mass. They stay hotter. The cold regions are devoid of mass. And what this tells you, actually, is that the universe is very smooth. And so it is more smooth than you would expect, given how clumpy the universe is today. You needed something that was really effective for moving you to these really small changes from hot areas to cold areas to galaxies and stars and planets and really dense clumps of material. Dark matter is the dominant force that allows you to do that. This size of this peak here tells you how much regular matter was in the universe. And if regular matter was the only thing that creates all the structure we see today, this peak would be like way up here. The fact that it's down here and tells us there's not much regular matter means that this is really smooth, and we need something really effective at making structure from non-structure. And the CMB actually tells us almost everything about how our universe starts. This is kind of an aside. It tells us how old the universe is. It tells us how fast the universe is expanding, this dark energy stuff you've heard about in the last couple of lectures. It tells us how much dark matter there is, how much dark energy there is, what the curvature of the universe is. Is it flat, or does it actually move back on itself? And that is all encoded in this diagram here, which is pretty amazing. Why is dark matter more effective than normal matter at producing structure, if this thing cooperates? Okay. The reason is this. Let's think about a lot of gas, and let's have it fall into a clump. Well, what happens? That clump starts to heat up, because all the gas had energy. It's falling in. It heats up. It can interact with the electromagnetic force. It can form things like stars. It can form things like dense plasmas. And that creates pressure, right? Those things heat up. They produce light. Light flows out, and it pushes all of the gas out again. So what you see, if you have a universe that has just matter in it, as things start to fall into a dense clump, then it produces a bunch of light when it heats up, and that pushes everything back out again. You get kind of a slinky effect, right? Things push in and out and in and out. So structure doesn't grow very efficiently when things can interact with light. Because every time structure tries to form, every time things try to collapse in, they get pushed out again because they heat up and produce light. Dark matter doesn't do that because it doesn't interact with light. So when dark matter falls into the center of a region and becomes more dense, well, it increases the gravitational pull, but there's nothing pushing out anymore because it doesn't heat up. It doesn't have that interaction that causes this seesaw mechanism. So if you want to go from the clumpiness, from the very smooth nature of our universe in early times to the very clumpy nature of a universe that we would see today, you need something that can very efficiently pull matter from non-clumpy forms into clumpy forms over time. This is kind of the key plot for why we know that there's dark matter and not some other force. Here's that harmonic effect that you would see if regular matter was the only thing contributing to how our galaxy clumps up and forms. You would see, in the universe today, you would not see very much clumpiness. Everything down here is low. And you would also see this harmonic behavior. Instead, you see the flat behavior, which is just an exponential, rich get richer, everything continues to fall in smoothly through all of history. So this is the picture of how the universe forms and how dark matter plays a role. You start in a universe that's very, very smooth, with very small initial fluctuations. It turns out, though this is a technical detail, that these fluctuations are a pure power law. So it's self-similar, like a fractal. There's little structure on all sorts of scales, from really big scale structure to really small scale structure, and that structure all has the same form. Then you have dark matter, and I'm going to skip playing that image. And dark matter is very efficient at falling into these denser regions. Any region that became a little overdense just starts growing and growing and growing exponentially. And that gives you a universe today with galaxy clusters, with galaxies, planets, stars. Everything is clumped due to dark matter. And that is what we're left with. So, there we go. From that, what do we think dark matter is? All I've said so far is it's something that has a lot of gravity. It falls into regions very well, and it pulls matter with it and forms the structure we see today. Okay. Well, the only object we're really good at seeing are stars, right? Stars produce light. We can count them up in the sky. We know how much they are, how much light there is from every star. We know how much light bigger stars produce. So we can count all the mass from stars very well. Maybe we're just missing something that forms dark matter. So let's go through all the options and line up the usual suspects. Okay, so maybe gas and dust. Like I said before, there's about 40 times as much gas or dust as there are stars that we can see. But remember from lecture 1 why this doesn't work. If I have a star way out in the distance and there's a lot of gas and dust, the light from the star moves through the gas and dust before it gets to me. And gas and dust, absorbs different frequencies of light very well. And so the light I would see when it gets to my telescope will have all these regions missing where the gas has absorbed things very efficiently. So I know how much dark matter there has to be to get everything to clump right and to create all the mass in the universe. If that was all in dust and gas, every time I looked at a star, I would see all this light missing. And I don't see that light missing. So it's not gas and dust. There is quite a bit of it, but not enough to make the dark matter. Maybe it's something called a massive compact halo object, called a macho. So maybe this is something like a big planet, a black hole, something that creates a lot of mass but not a lot of light. Right? Planets are hard to see because they don't have nuclear fusion. Black holes are hard to see because they're black. So maybe there's a lot of these objects. We don't know where they come from, but if there's millions of them in every galaxy, they'll produce extra mass that we can see. Well, this is where that gravitational lensing comes into account, right? These things will be flying through space in random directions, and they'll lens things that are behind them, stars that we can't see, right? So every time a massive object moves between us and some background star, we'll see some sort of Einstein ring, or we'll see the star get brighter. And then when we see that, we'll know that something passed in between. Well, we can count up all these gravitational lenses that happen. And it turns out that there is not enough gravitational lensing for if the dark matter was really point-like objects that were really heavy. There's a lot of gravitational lensing from dark matter, but the clumpier the dark matter is, the more lensing I expect. The more strong lensing I expect, because these things are really concentrated particles with lots of mass behind them. I'm going to run up and show one more video because it's really cool. This is a black hole. This is a black hole that's passing in front of a nearby galaxy, and it's gravitationally lensing everything nearby it. You see as it moves right through the center of the galaxy, not only does the galaxy get warped into a sphere, but it also becomes brighter. And it becomes brighter because light that was going to miss you going off in every direction gets bent back towards your telescope, and you see it suddenly. So that's called microlensing. Even if you didn't see any of this warped shape, which is pretty obvious in this picture because this is a nice simulation, you'll see background objects suddenly become much brighter when lensed objects pass in front of them. Apparently that's how I extracted that image. Okay, so you can look for all these objects that suddenly become brighter when objects like a planet or something passes in front of them. You don't see many of those, and so you know it's not massive objects. It has to be something that's very light on an individual particle level. Okay, let's take a step back here and make sure that we're thinking about a new particle correctly. So there was an idea started in the late 80s called MON, Modified Newtonian Dynamics, started by Mordecai Milgram, who said maybe what we don't need is dark matter. Maybe just how gravity works is we haven't figured it out, right, and we're making a mistake. So what he proposed is that at really small accelerations, when you're really far away from the center of a galaxy, right, the force from every other star that's pulling you in is very, very small individually. So maybe you need some modification in how strong gravity is at really large distances and really small accelerations. And it turned out that that explained this curve quite well. What it didn't quite explain, and why this idea is mostly rejected, is it doesn't explain things like the bullet cluster anymore, right? Because here, where the gravity is not even close to where the gas is anymore. So it can't be really small modifications because it's just not in the same location anymore. It can't be coming from the baryons. Also, for all these suggestions that I just proposed, planets and gas and some sort of modification of how baryons work gravitationally, remember, I still have this problem where baryons can heat up when they get close to each other. And they create this harmonic structure, right, where things get more dense and less dense and more dense again. I really need something that doesn't interact at all. So that's going to push me in a really new, interesting direction. Maybe it pushes me in the direction of something like neutrinos. So neutrinos are a particle that we already know about, right, that is weakly interacting. It doesn't interact with, neutrinos, they don't interact with light at all. So I have neutrinos passing through me at about 100 million per second or something like that, mostly from the sun. They're produced in the fusion of elements in the sun very efficiently, and then they move off at mostly the speed of light. Neutrinos were first proposed in 1930 and discovered in 1956. They were proposed to be due to the following process. How does a neutron break down into a proton and an electron? Well, it turned out that this was, for a technical detail, a spin-half particle. And these are both spin-half particles, and 1/2 can't equal 1/2 plus 1/2, or 1/2 minus 1/2. So you needed a new particle here. And so Pauli, I think, or Fermi, one of the two, proposed that you needed a third particle to make all of the spin states work. And he proposed this, and then they found it as an additional particle in the decay of neutrons and heavier elements. So one interesting thing about neutrinos is we don't actually know how massive they are. It was thought actually until about the 1990s that they could have no mass whatsoever, just like a photon has no mass. But it turns out, for some technical reasons, that neutrinos can oscillate between different types of neutrinos, and thus they do have mass. But this mass has to be very, very small. We don't actually know the mass of any individual neutrino, but all three of them together are less than 0.32 electron volts. By comparison, an electron is 500,000 electron volts. So these are like, 1/100,000th of the mass of an electron, which is itself 1/1000th of the mass of a proton. So very, very low mass minute particles. So these could be the dark matter, though, right? There could just be lots and lots and lots of them. Even though they have little mass individually, there could be tons of them that can make the dark matter. They're perfect because they don't interact with light. They only interact via this weak force, and so they can't do the bounce back, right? They will stay cool as they collapse into dense structures. The problem with neutrinos is the dark matter. This was a one of the most reasonable things to think dark matter was for a number of years, is that neutrinos, like I said, have a very, very low mass, which means, remember the cosmic microwave background, when that separates, it was very hot. It was about 4,000 degrees Kelvin. And at 4,000 degrees Kelvin, something that has very low mass has to move very fast, right, to have kinetic energy. So when everything separates out at the time of the cosmic microwave background, neutrinos are moving near the speed of light. And this creates a problem, because I have a gravitational potential well I want to form, right? And I want everything to fall into it effectively. But if everything is moving at near the speed of light, it doesn't collapse well, right? Just like if I shoot this laser off, it doesn't bend off back towards the Earth because it's moving so fast in the other direction, right? So neutrinos weren't able to form small structures and build up because they just move right past each other. They could form really, really big clusters because those had lots and lots of mass in the center. So you could form the really, really heavy galaxy clusters, but you wouldn't form any of the smaller structures, things like galaxies that we see today. You'd only form the really big things. So here's what the distribution of galaxies looks like near us, some random sampling of galaxies. There's some clumpy galaxies here. There are some that are more spread out. Here's what it would look like with neutrinos. You would see some really, really large clumps of where galaxies form, and everything else would be empty and void-like. And so that's how you would rule out these sort of hot dark matter neutrino scenarios. That suggested to us that dark matter has to be cold. And by cold, I mean at the time of the CMB, it wasn't moving too fast. That way, it wasn't moving very quickly, and it could fall in and form dense clumps effectively. It could form small clumps, and those small clumps grow into bigger clumps, like we saw in that simulation a minute. So let's review what we just learned and say, what are the properties that any dark matter particle has? Well, first it has to be dark. It can't interact with the electromagnetic force. If it does that, it will start collapsing, and then it will heat up, it will produce photons, and it will uncollapse. And it won't be able to grow structure effectively. So we know it's not that. It has to be stable, by which I mean it had to exist very early in the universe, and it still needs to exist today. So it can't be like, having some sort of nuclear decay into other particles. It can't, keep changing forms in any way. It just needs to be a stable particle that can sit around and interact gravitationally. It can't be very massive. It can't be so big that it creates a lot of gravitational lensing that we don't see. So it can't be like the size of, I think what's ruled out is the size of the moon up to the size, 100 times the size of the sun. I think all that's ruled out by the gravitational lensing experiments. So it can't be massive things, but it can't be very, very light either, by which I mean it has to be relatively cold when the CMB separates, so it's not moving quickly, and it can form small structures. Those are what we know. So in the next lecture, I'm just going to kind of tell you what I'm going to talk about next week, which is 3 types of proposed particles that have those characteristics, called axions, sterile neutrinos, and WIMPs, as opposed to MACHAs, weakly interacting massive particles. So that's going to be the lecture for next week. And I'm going to talk a little bit more today about some of the gravitational tests that can be performed now that can tell us more about how dark matter works. So dark matter plus dark energy is incredibly good at explaining how the universe works on large scales. So how galaxy clusters form, how many galaxy clusters there are, what the different masses of galaxy clusters are supposed to be, how the CMB has hot and cold points. Those are all miraculously fit by dark matter. If there were error bars on this graph, they would all be smaller than the points. Where dark matter starts to, I would not say have problems, but where there are uncertainties in our measurements, is when you get down to small structures. So here's cosmic scales, cluster scales, everything is perfect. Here are those baryon acoustic oscillations of how matter bounces back and forth. They create really small wiggles even in the presence of dark matter, and we match predictions with those. But when you get down to galaxy scales and things that are smaller than galaxy scales, you have to worry about additional factors. When you get down to really small structures, you have to worry about, is dark matter hot at all, and will it not form really small structures? What are all these baryons doing, right? What are all the stars doing? Are they heating up dark matter in some way? And what does that do? So the first question is, what does the profile of dark matter look like? What does the density of dark matter look like as I go in towards galaxies? And if you remember those original curves, which I should have put on this plot, but I didn't, dark matter controls how stars move when you're really, really far away from the center of, say, a galaxy or a galaxy cluster. Because most of the mass is from dark matter. But in the center, I said most of the mass is from baryons. And the reason is because baryons can form frictionally, they can cool down, and they can form disks that get really dense in the center of galaxies. Dark matter doesn't have a frictional force. It doesn't interact with light, and it can't do that. So most of the mass right at the center is baryons, which makes it hard to measure how much dark matter there is. It's not a dominant gravitational force, say, in the center of our galaxy. So how much is there is hard to measure. It's within the uncertainties of where all the baryons, by the way, when I say baryons, I mean protons, neutrons. I'm also counting electrons, which are technically not baryons. They're leptons, but they have very little mass, so they don't actually matter. So this is a calculated profile. If there was just dark matter in the universe, the dark matter profile would look like this. This is the density of dark matter on this side, and it has some constant density for whatever galaxy you're looking at. And it is divided by the radius you are away from the center. And that's the most important part. So as you get closer, it diverges. It goes up as 1 over r. And it gets steeper and steeper towards the centers of galaxies. So this is the density of dark matter. We're out here. This is us at 8 kiloparsecs away from the center of the Milky Way. And the density will get higher and higher as I go towards the center of the galaxy. Unfortunately, the density of stars goes something like this, stars and gas, which means that dark matter is important out here, but it's not important in this really inner part. This was calculated by Navarro-Franken-White, and is called the Navarro-Franken-White profile. This is also a Navarro-Franken-White profile. Good joke. They've posted like 7 pictures like that. Like every year someone asks them, and they are good sports, so they do it. But there are also other profiles that have been calculated by various groups. So the Navarro-Franken-White one is this one in red. There's one that was done by simulations called INASTO, which is this profile here in blue. There's something where the profile cuts off and becomes constant. This is called a Berger profile, where the density never gets high in the center of galaxies. These all have very similar gravitational effects on, say, stars really far away from the center of a galaxy, because everything out here matches. But it's really, really different in the center, and that's going to be important when we start talking about how do we detect dark matter later. This is a more technical slide. We want to calculate now how this dark matter forms in the center of galaxies. So we look for these really small effects that the dark matter here might have on stars. And people are starting to calculate, this is kind of cutting edge research, so I just put a lot of plots on what the dark matter density is in these units here. We think near the position that we are in the galaxy. So we look at all the stars that are really close to us, and we look for small perturbing motions in the stars as they move up and down from the disk of our galaxy. So all the mass of the galaxy, most of the stars are in this disk, but dark matter forms this kind of halo. It's spherical around the disk. And so how far up stars move above and below the disk depends on the amount of dark matter compared to the amount of luminous matter we can see. And so when you calculate this, you get some number for the amount of dark matter near us. And that's all I really want to point out on this slide. Okay, so what are all the baryons doing in galaxies? Well, baryons, unlike dark matter, can cool. So if you think of what's happening, right, I have dark matter is forming some clump. And all of the baryons, all the protons and electrons start falling in because the gravity from dark matter is pulling them in along with it. But then you have some direction where everything is kind of rotating preferentially, right? Because everything is falling in, it starts rotating faster and faster, like a ballerina pulling in her arms, or an ice skater, or something like that. Things can't fall in this direction because things are spinning in this direction, so they push things out. So, but baryons can continue to fall in this direction. That's why galaxies kind of look like pancake shapes, right? As they start spinning fast in some direction, which is randomly chosen, things can't fall in along the spinning direction, but they can fall in the other direction. So gas and stars continue to fall into the centers of galaxies and form these disks. When that happens, they heat up. They form stars. They have supernova explosions, which inject a bunch of mass suddenly. And these all create changes in the gravitational potential. So as I collapse and form a star, right, that changes how gravity is oriented, nearby that star. In dark matter, even though it can't interact electromagnetically, does interact gravitationally. So once baryons become important in the center of a galaxy, dark matter has to follow all of these new perturbations, right, that the baryons are producing. So when there's a clump from a black hole, the dark matter is going to, get pulled in near that black hole in the same way that gas or dust would. So in our beautiful picture of just dark matter that we had formulated earlier, it was very easy to calculate. There was no electromagnetic forces, there were no supernova, there were no black holes being formed, anything like that. It was just this beautiful picture of a bunch of really light particles. Massive regions get more massive, lighter regions get more light, less dense, and things continue. Once you put baryons and all these complicated light-based interactions in, the picture gets convoluted. And it's very tricky to calculate, and this is kind of what we do big supercomputer simulations of now, how all of that feedback affects the dark matter, and how the dark matter continues to affect the baryons. And this back and forth gets very complicated in regions once you can do complicated things like form stars and stuff. There are observations that tell us a little bit about dark matter in our own galaxy of dwarf galaxies, which I don't think Keith mentioned in his talk, although he also works on this quite a bit. So we have a bunch of dark matter in the Milky Way. We can calculate how that perturbs stars. We've also found substructure of dark matter. So if you saw that picture, there was a big galaxy cluster right in the center. That's where most of the dark matter was. And then there were all those bright spots that have galaxies. And if you could have zoomed in, all of those bright galaxies would have had their own little bright spots. And those you would call dwarf galaxies. Everything is self-similar like a fractal. So the galaxy clusters have galaxies. The galaxies have galactic subhalos. The subhalos have substructure, and it just keeps going down like this. So we've actually found these dark matter subhalos. So these are small dark matter-dominated regions of the sky, and they all are, rotating around the center of our galaxy. You'll see they're mostly up here, and the reason they're mostly up there is because that's where the telescopes have looked. It's not a detail about how these things are actually oriented in our galaxy. It turns out they're easy to spot if they're far away from the center of our galaxy, because this is really bright, and we have telescopes that look for them in the north and not so many in the south. So that's where they are. And what happens is, so this is a dense region of dark matter somewhere in our galaxy, and there are some stars that are around too, just a few, and those stars start orbiting around the center of that dark matter, so they get peculiar velocities. These things are all orbiting the center of our galaxy, but then the stars then are both orbiting along with these things, and so they get weird circular orbits. So if you look at enough stars, you can calculate where are stars orbiting in some weird circular pattern around the center of something, and you calculate how much dark matter is there. Interestingly, there's some evidence that that Navarro-Frank-White profile that I pointed out doesn't work particularly well in dwarf galaxies. That this profile, this is how much mass there is in different regions as you get closer and closer to the center of these dwarf galaxies. This is the Fornax dwarf galaxy in particular, which is somewhere on here. Oh, there it is. You would expect that this thing would keep increasing. That's what Navarro-Frank-White predicted. And instead, this recent paper, which is just from like a year or two ago, so who knows if it's, the final word on things, shows that the dark matter density doesn't increase as you get very, very close to the center of dwarf galaxies. So maybe that's indicating something interesting to us. Maybe it indicates that baryons are playing some important role and they're pushing dark matter back out when they form supernova or something like that. Maybe it says dark matter isn't really, really cold after all. If dark matter is a little bit warm, then it won't form those really small substructures. It'll only form bigger structures. And then you wouldn't expect, to get really dense areas in the center of these dwarf galaxies. And maybe it indicates something else completely. But that's an active area of research. The last question is, well, like I said before. There's galaxy clusters, and they have substructure, and those substructures form galaxies. And then those have substructure, and those are the subhalos. And then those have substructure with the thing. The substructure gets harder and harder to see. How far down does the rabbit hole go, right? And finally, there must be some point where you have individual atoms, or not atoms, individual particles of this dark matter, and it can't form substructure because it's one particle. But how far do we go towards that limit? And this actually matters a lot for some of the ways that we detect dark matter. Because if we have denser and denser, but smaller and smaller substructures, we might be able to detect those through basically the particles in them crashing into each other and annihilating, which is something that we'll talk about in future lectures. But it's important to understand first how far down the substructure goes, which is a question really of how hot the dark matter is. Is it really, 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 really cold? Is it a little bit warmer? How is it interacting with baryons? We want to know all these questions. And so continuing to probe for basically smaller dwarf galaxies and maybe substructure within dwarf galaxies can tell us that. So I'm going to end the lecture here at this point for today. And just kind of as a takeaway, we know that dark matter controls how the universe evolves. It matches observations perfectly going from that CMB, very smooth universe, to the very clumpy universe we see today. And that's just a gravitational interaction that dark matter has. It hasn't told us anything about what the particle responsible for dark matter is yet. That's something we'll have to determine by how dark matter interacts with other particles on a particle-by-particle level. And that's going to be the topic of the rest of the talk. So next week I'm going to talk about 3 of the different particle components: axions, sterile neutrinos, and mostly weakly interacting massive particles, both because that is probably the most accepted view of what dark matter should be, and also because it's what I work on. And then for the next couple lectures, I'll talk about how we could detect a weakly interacting massive particle, either through observations in space, observations deep underground, or in particle accelerators like the LHC. Thank you.
You can turn the room lights up now.
Yeah, sure. Do people have questions? Yeah.
Apparently, like neutrinos go through regular matter with very little interaction. What about light going through dark matter? Is there any interaction, or do you see any absorption of light by dark matter?
Right. We think that dark matter doesn't interact with light, so it has that same property that it goes straight through matter. So just that, like we know that there are 100 million neutrinos moving through every second. I think that's the right number, but I don't know. We think that there are thousands of dark matter particles moving through you every second. I mean, when these don't interact with light, they just move straight through. Because every interaction that something would have to, hit an atom or a cell in your body requires some light being exchanged or some sort of excitation of photons. And since it can't do that, they just, they go straight through. Yes?
Is it relevant to ask about the interaction between a black hole and dark matter?
It is. So how do we think black holes form in kind of the standard picture? It's a really massive star. Fusion stops, the star starts to collapse. There's a supernova explosion as things heat up during that collapse. But what gets left is there's no support from nuclear fusion anymore, and there's a lot of massive things falling. That, we think, mostly includes baryonic matter. I mean, the star was mostly protons, neutrons, electrons. What's left is protons, neutrons, and electrons. Once I have a like a large clump of mass that form this black hole, dark matter that moves nearby will get pulled in, or can get deflected, or could get pulled all the way into that black hole, the same way that gas or dust that gets too close to the black hole. So it turns out that every black hole should have some dark matter in it. If you do the calculation, it will be a very small portion of the total matter. And part of the reason is how does most gas fall into a black hole? Well, it starts getting cooled around in a circle, right, and it starts spinning. And then you form this kind of dense accretion disk with a bunch of gas orbiting the black hole. Two gas atoms can crash, and one will get knocked down and won't get sent into the black hole, right? Just like if you put a one of those coins on the little rotating, what do you call it? The little, I don't know, mall, right? You put a coin in it and it spins around, right? There's frictional forces that cause the coin to go lower and lower and lower. And gas can have that frictional force. Dark matter can't, because it doesn't interact with light. And so it will spin for a very long time around the black hole. And it could just spin forever without interactions. So it's unlikely that there are collisions which will send it into the center of the black hole. So you really have to have a dark matter particle that goes right directly in. Just like if you threw the point directly in, it won't spin around at all. No, back left. Yeah.
Oh, yes. In relationship to Einstein's theories, does general relativity work for dark matter or not? And does E equal mc squared apply to dark matter and dark energy or not?
Yes and yes.
Oh, good.
Yeah. So as far as we know, general relativity works for everything that has mass. It's a question of how an energy density in one place, which could be dark matter or dark energy or just regular baryons, creates a curvature of space and everything that's nearby, or everything in the universe overall. So that works for dark matter the same way as it should work for anything else that has an energy density. And what was your first question?
The other part was E equals mc squared is
Yes.
equally applicable to dark matter and dark energy.
Yeah, and we think that everything, all fields, whether it's something that creates dark matter or something that creates normal particles, has an energy, and you can, go between those with E equals mc squared. That would actually be important for weakly interacting massive particles, which we think can annihilate, produce pure energy, which would be 2 times their mass, and then, produce normal particles that we could see.
Thank you.
Yeah.
If dark matter is in a halo near the edge of around the sphere around the galaxy, it must be moving very fast. How does that affect the proper motion of stars near the halo and closer into the center of the galaxy?
Yeah, I skipped the plot. Okay, this is a calculation here of how fast dark matter is moving around the center of the halos. This is the velocity times some function that you don't care about. These are different velocities here in kilometers per second. So 200 kilometers per second up to 550. On this plot, it's just shown the whole thing from 0 to 600 kilometers per second. This is how much dark matter there is at these different velocities. So most dark matter is moving in our halo at 200 to 300 kilometers per second. But remember, in terms of affecting stars, the dark matter mostly just passes right through the star. It's very bad at exchanging momentum with stars because it can't do that by exciting photons and creating interactions. So for the most part, the effect is actually very small. Where it comes in a little bit is that the galactic plane, has most of the mass from stars in a very thin region. It's about 100 parsecs bottom to top, and as opposed to about 20,000 parsecs this direction along the plane. Dark matter is spherical, we think. And actually, we can calculate that because it doesn't have that ability to start spinning. Well, it'll spin in a circle, but because it can't interact frictionally, things can continue to fall in along that direction of rotation, which baryons can't do. So dark matter is spherical, and that means that the gravitational potential deviates less above and below than if it was just stars and just the plane. So if you find a star that's moving up a little bit above the plane, eventually the mass from the plane will pull it back down. But how big these wiggles are depends on the amount of dark matter above and below also. So it's a very sensitive measurement because it's a small, fractional deviation in how these stars move up and down.
And it decreases as you get closer to the center of the galaxy?
Yeah. Basically, the dark matter density increases near the center of galaxies, but not as fast as stars. Stars increase much faster, and so dark matter becomes fractionally less important the closer you go towards the center. Yeah.
Is there still work on the possibility of some kind of a modified theory of gravity explaining some of this? It seems to me that it's a little bit artificial to assume that so much dark matter is in the halos at the edges of the galaxy. And it suggests at least a possibility that maybe some of this explanation for some of these effects could be a modified theory of gravity.
Yeah. So that was the MOND theories that I mentioned briefly. There are still active researchers who work on this. It's certainly a minority of researchers. And the reason is really these, first the Bullet cluster observation, where the dark matter doesn't appear to be in the same place. And also that observation that if everything that has mass is allowed to interact with light and heat up and cool down, then you get these, matter starts to collapse and then it heats up and there's a pressure wave that expands it again. So you get these acoustic oscillations in space. Things collapse, reheat. At this point, the modified theories of gravity don't have good answers for either of those observations. They have very good answers, or that the theories fit the data very well for how stars move far away from galaxies. That's not really a problem for MOND theories. But Bullet cluster and acoustic oscillations are really difficult to explain. I think until they have, maybe someone proposes an explanation that really works for those, and then I think people will start taking it seriously again as a major research program. But right now it's a minority for those reasons. You've asked. Yeah, sure.
Quick question on, is the gravity that dark matter produces, you're hypothesizing a lot of things about it based on its gravitational effects. Is that the same as the gravity in regular matter? And does regular matter and dark matter, are they mutually, they mutually attract each other? Masses?
Yes. Yeah, we think, gravity is really defined by Einstein's equations. So all it says is if you have an energy density here, whether it's dark matter or regular matter or some sort of dark energy, it doesn't matter the form. If there's an energy density, then space curves around that energy density. And that doesn't matter that doesn't matter gravitationally whether it's dark matter or regular matter. So all of the gravity effects are the same. It just doesn't have any interaction with light. That is a different force that's different between baryons and dark matter. Yeah?
Are there other objections to neutrinos being dark matter than the fact that they'd have to be moving fast? Or that they are moving fast?
Yeah, that is by far the major problem. The other thing that you can calculate how many neutrinos there are, order of magnitude in the universe. And so, depending on what the neutrino mass is, if the neutrino mass is really, really, really small, then the number of neutrinos won't produce most of the mass in the universe. It wouldn't be enough to make the dark matter. But on the converse, it was actually proposed that a lot of the neutrino masses that people were guessing would actually form too much mass in neutrinos and the universe would collapse back on itself, which was bad. So we think neutrinos have to be really light. Once we get that measurement down in the future, we'll know what percentage of the extra mass they could make up. We think it's very small, but we don't know that for sure. So the major thing is just structure. And neutrinos could be a small component of dark matter. So you could have a small, neutrino portion, which changes maybe how, really big things form versus very small things. That's a possibility that's open right now. But it doesn't look like it can create most of the dark matter and make a universe that looks anything like the one we see.
Yes. Neutrinos change in flavor, apparently, as they move along. They also change in mass, which would indicate some sort of a variable. Is there any indication that neutrinos had greater mass in the past?
No indication of that. I think that would violate energy conservation. If you have E equals mc squared, then you can't have m changing without it getting energy from somewhere. So you could have probably some theory that slightly violates energy conservation over time. It still explains observations and stuff like that. But as far as we know, the neutrino mass stays the same. The oscillation of neutrinos part. I remember how this works for mass eigenstates. The flavor eigenstate of neutrinos is not the same as the mass eigenstate, and that creates some complexity in what you're saying. But I think in general, I think that's the answer. The neutrinos we don't think change in mass. Yeah.
Since the Big Bang Theory was developed without dark energy and dark matter, which is not insignificant, shouldn't it be revised again from the beginning instead of just patching on theoretical structures to a theory?
It was created, you're right, without any mention really of dark energy or dark matter. We knew that the universe was expanding, a fact that we now, what they knew was that the universe was expanding. And so you just point the tape in reverse, and you got to a point where it had to start somewhere, right? That's what you had decided. And you called that the Big Bang. We now know that that expansion is primarily due to dark energy. We didn't know why at the time. We just had the observation. So we already knew about the expansion of the universe to make the theory. It turns out that dark energy and dark matter, I would say, lend itself to a Big Bang type theory rather than making us change our paradigm. They explained why some of the changes in our universe, starting from a very small homogeneous state to the universe we see today, actually work.
Okay. Thank you.
Other questions?